Okay, when we talk about conservation of energy, it's going to be one of the approaches that is available to us when we are, looking for or where we have or we're dealing with velocities and displacements. So we know, I'm going to start actually down here using the work energy theorem that work is going to be equal to the final kinetic energy minus the initial, or the difference, the change in kinetic energy that occurs. We can say that very same thing for potential energy, where we can say there is work done when we have gravitational potential energy. Okay, so if we look at that difference in potential energy, that can also give us what the work is of a system. Now, knowing that both of those equal work, we can rearrange algebraically so that we can say on the left-hand side here, the kinetic plus the potential energy in the initial state. That is gonna give us what is the total amount of energy that is available. It's going to be equal to, in the final state, whatever is left over, in terms of kinetic energy plus its potential energy. Okay. Now, what this says is that all of the energy that we have to start is going to equal all of the energy that we end up having in the end. Okay. We can't have any more. We can't create any more energy through that. That's called the conservation of energy. And that's a law, right? Sometimes those values might not line up, but it's because of losses that we would end up having in that system as it's doing the work that it's doing. Okay. So a lot of times, as I said earlier, especially in your physics experiments that you would have done to show these relationships and concepts and prove them, if you would, there would be those differences between the theoretical values and when you actually, gathered your data and calculated everything was, should have lined up, but there was differences. And those differences usually came from losses in the system. And one of those main losses is going to be friction. When two surfaces are going to be working relative to one another, rubbing up against each other, heat is created. So that is thermal energy then that comes off of that system. So that was part of the original work, if you would. So as we did that work, it converted over into other forms. And one of those forms is going to be heat. Another one is audible. So sound energy is something that comes from that original pool of total energy that we had originally too. So if we hear anything as, elements are going to work relative to one another, that is also going to be pulled from the original. So sometimes we forget about that sound energy, but thermal and sound energy are two of the biggest losses that we see from the original to the final state when we look at energy. Now, potential energy, we haven't really talked about yet in dynamics here, but I know that you've come across it in, like, for instance, your physics class. Potential energy stored at the top of, for instance, a ball's path is transferred to kinetic energy as that ball meets the ground. But as it bounces, couple things are going on. Those two things that we just talked about. Sound energy is dissipated as well as friction is also dissipated. So each time it takes another bounce, you're going to notice it's not going to go as high as it was before because it lost something in that bounce. And then now it can only go as much energy that it has left over. When we talk about potential energy, the most common one is going to be gravitational potential energy, and that is energy that something has due to its elevated state. Okay. Now, to calculate potential energy, gravitational potential energy, we're going to take the mass of an object times gravity, which is going to equal, if we multiply those two things together, that's the weight of that object, multiplied by the height that it's at. Okay. And that's going to give us the total amount, if you would, if it's at its highest elevated state, that's going to give us the, maximum amount of potential energy that this item is going to have. Now, the force that does the work then in gravitational potential energy is going to be this part right here. And when it's the mass times gravity, it's its weight is going to be doing that work. Now, when we look at the direction of the weight, especially when we're going down an incline, you have to be careful Remember, work is done in the same direction that the force is being applied. So our work is a vertical force, okay? Even though it's going down the decline here or this ramp, the the distance that we need to measure to line up with how much work is done is going to be the vertical distance. So again, the force is vertical, the distance has to be vertical. Okay, it wouldn't be along the path. You wouldn't do this distance here. It has to be in the same direction as the weight. So multiplying the weight times the height or that distance that was covered, that's going to give us the potential energy that we have. Okay. Now, if we look at the original potential energy and we subtract off the ending potential energy, that difference between those two is going to give us the work that is done. And that happens because of the height changing. So if our initial height is higher than the ending height, then that means that we lost potential energy through that process. Now, does that mean that we lost it completely? No. What it means is that it was converted into something else. And most often, that conversion is going to be, or most of that potential energy is converted into kinetic energy because now it's probably speeding up as it's going, as it's falling. Okay. So it doesn't mean that we lose anything, but that difference constitutes the work that's being done. Okay. Now, choice of the datum from which the elevation y is measured is going to be something that you determine as the, overseer of the problem, if you would. We're going to be setting a datum or a baseline, if you would, where our numbers are going to be referenced from. And then throughout the problem, that remains kind of that base where we continue to go back to. And we're going to do that in the problem that we work illustrating the conservation of energy. Then the last concepts that we want to add or talk about and then add to our equation sheet are going to be power and efficiency. We did touch on this in, I think it was in chapter 17 in module 3, but as a review, power is going to be the rate at which or how fast work is being done. So capital P for power is going to be equal to work, U1 to 2, divided by how much time it took to do that work. Or we can also use a force multiplied by how fast it's going, what its velocity is, okay? Now, the units for power are going to be, in the metric system, it's the watt. And a watt is a joule per second, or a Newton meter per second is a watt. Now, you may have heard terms like kilowatts. That just means that that's 1,000 watts, okay? Now, if we're in the English system, we're going to be dealing with horsepower. Horsepower is 550 foot-pounds per second, okay? And to convert it over, if you want to know what it is in watts, it's 746 watts, okay? So, but if we are in English system, it's foot-pounds per second, or a horsepower, or 550 of those is a horsepower. Or if we're in metric, it's going to be a joule per second or a Newton meter per second, which is a watt. Now, lastly, we're going to be touching on efficiency as well. Efficiency is how well work is done. So what we do for efficiency is we figure out, or we determine, what is the output work? So how much usable work did I get out of our system? And we divide that by how much work did we put in? Okay. And by doing that, we're gonna get a decimal number. All right. That number will always be less than 1. And the reason it's less than 1 is because I can't get out any more work than what I put into the system. That would be a violation of our conservation of energy law. And like I said earlier, the difference between this input and this output work are the losses that we see in the system, like friction, sound, those types of things, the heat, the thermal energy that's generated. Now, not only can we do this comparison with work, but we can also do it with power. So we can say the output power divided by the input power is going to give us the efficiency as well. So again, comparing how much power we're putting in to how much that we're actually getting out. Okay. So let's go ahead and finish up our equation sheet with the concepts that we just talked about, and then maybe a couple more as we go along. And then we'll get into our next problem. So I'm going to go back underneath my camera. Okay. And you're going to notice that we're going to continue on below our weight and friction. And what we're going to add here is going to be the conservation of energy. Okay. And we know in its like simplest form, it's going to be T1, so the kinetic energy initial, plus V1, which is our potential energy. It's going to be equal to T2 plus V2. Okay. Now, we can expand out the potential energy into two different forms. So T1 plus V gravitational, I usually do a GR, okay? And we would call that 1 because it would be its initial state. And then if we have any potential energy due to a spring, we can add that in there. It's going to be equal to T2 plus, again, V gravitational 2 plus V elastic 2. Okay. Now over here, VGR is equal to potential energy. Okay. And we know that to be calculated using MGH. All right. Now, elastic kinetic energy. Okay. I'm sorry, potential energy. So elastic PE is going to be equal to 1/2 kx squared. Okay, so that's the equation for the potential elastic energy when and if it's present. If it's not there, then we just don't consider it, just like we did earlier with the work. All right. And then I am going to go to my next section, which is going to be power and efficiency. We want to add those. Those are also come in handy. Okay. So P is going to be equal to F times V, so force times velocity. It's also equal to work done divided by time. Okay. Now, I think we all know what all of these variables means, right? So P is for power, F is force, V is velocity, work, and time. I'm not going to write those over on the side here. But the units are going to be equal to the watt, which is equal to a joule per second, which is equal to a Newton meter per second. Okay. And if we're a horsepower, 1 horsepower, that's equal to 550 foot-pounds per second. So foot-pounds per second. 550. Efficiency, okay, that is equal to the work out divided by work in, or power out divided by power in. Okay, and this unit is efficiency. Now, no units for efficiency because the same units would be top to bottom, which would cancel out. We get a decimal value, and you can multiply it by 100 to get, for instance, a percentage of efficiency. Sometimes we say 85%. So then whatever decimal we get here, we would multiply that by 100 to get to the percent. And then the last thing that I want to add down here that's going to come in handy is the calculation for percent change. You probably have done this in like physics class, like when you were trying to decide like how much different was it from, state 1 to state 2. And they just don't have it in the book here, but we end up using it for a problem or two. So I want to be sure that you have it. So the percentage for state number 1 plus the percentage for state number 2 divided by the initial or state number 1 percentage. Okay, so that'll come in handy in one of our problems. Okay. Now I'm going to turn this over because there's just a couple other things I want to add here. That was concept wise, but another thing that's going to come up is we need to just remember normal acceleration. It's actually going to be in the very next practice problem that we do. Okay, normal acceleration. So you could look back on previous modules for this equation. It's there, but rather than having to go through, why not just add it here? It's going to be velocity squared over your radius of rotation. So this is going to be normal acceleration. The units are going to be, as we know, meters per second or meters per second squared or feet per second squared. And then rho, I think, is the Greek letter. Rho is radius of rotation and or radius of the curve. It's going to be equal to mass meters or feet. Okay. And I think that's it. I think that's it. If we need to add a little something, we will, but I think that covers everything that we need. Okay. So putting this aside, what I want to do is I'm going to stop the recording here, but then we're going to start again with the next example that we're going to be doing for our practice problems.